So what is Cartesian vector notation? Cartesian vector notation is simply deconstruction of a vector. So we had a resultant vector on this experiment pointing straight up, and we can deconstructed it out of its component along this line, component along that line. If we all deconstruct to the same components, then we can talk to each other. That's Cartesian vector notation. We can take any vector in the world, and we can break it up into its x, y, and if we're in 3D, z components. And then we can give that information to someone else, and we can talk to each other and figure out how one vector fits with another. So for Cartesian vector notation, we make up some vectors that we want to use to communicate. And those vectors are called unit vectors, and they are along the x, y, and z axes. Along the x-axis, we make a little unit vector pointing along the x-axis with a magnitude of 1, and we call it I. Yes, that's how I write an I. I apologize if that looks like a J to you. A J would be looped the other way. And this is a unit vector along the y-axis called J. So the idea is that we can separate out direction from magnitude if we use a unit vector. And we can say, okay, it's this far in the x and this far in the y. So we resolve each vector into its components. You see there's 3 vectors on this picture to the left. If we were to take, let's say, f1 as a vector, pay attention to the notation here. If f1 is a vector, that's going to be equal to the component of f1 in the x direction, f1x times I plus f1y times j. So we're taking the vector, we're breaking it up into a little bit in the x and a little bit in the y. We can do that to all 3. f2 is equal to f2xi plus f2yj. Now some of you might look at f2, which is over here, and say, shouldn't it be minus f2, or shouldn't it be minus f2xi? Because it's going the negative x direction. That's a common question I get. And what I recommend is that you store your negatives within your variables. Okay? What do I mean by that? I mean, instead of writing minus f2xj or f2xi, I would later say that f2x equals negative 5, or whatever it ends up equaling, right? The negative 5, the whole thing is going to be stored in f2x, so this remains a positive. Why do I recommend you do that? Because I find that lots of times students will pull that negative out and then later forget they did. So if you pull that negative out and then you solve for f2x a page of work later, and you get a negative number, you report it as a negative number, when really it should have been a positive. Does that make sense? So I recommend just storing the negatives with your variables. Okay, and then I would have f3 equals f3xi plus f3yj. So then my fr, basically what we've done is the second picture. In the second picture, we've taken each of those 3 blue vectors, and we've made each vector into 2 vectors. So now we have 6 vectors. Each vector has just a y or a j direction. Then we're going to add up those 6 vectors, 3 in the x and 3 in the y direction. And when we do that, we're just going to end up with f1x plus f2x plus f3x all times I plus f1y, f2y plus f3y times j. This is considered full Cartesian vector notation. We write stuff in front of the i's and j's, and we write the harpoon over here to say that we're storing both direction and magnitude on this side. Okay. Another way to write it is in scalar notation. Very good question. So f2x is a scalar variable, right? We're putting the x in there as kind of a convenience to remember that that is in the x direction. So that's a scalar variable. It just has no direction in it. We will replace this with 2. Exactly. And then the I is actually a physical vector. It's a vector that goes in that direction. So I is not a placeholder. It's not notation. It is a physical vector. We're taking a number, multiplying it by a physical vector, and another number by a physical vector. Another option would be, instead of having f2x and f2y, we just have like f and g, right? The problem with that is you can kind of lose track that both of those came from f2. So that's why we do the notation like this. The other way to write it is in scalar notation. In scalar notation, you still have to indicate your direction. But you kind of take it out and put it in the front. If you're going down your page, this would be on the very first thing you write on a line. I would say, well, everything in this direction which is the x direction. And then I'd say in that direction, frx equals f1x plus f2x plus f3x. Are any of these vectors? No. These are all components of vectors, and this is part of what you were asking. Now it's easier as we go down our work to remember that they came from the x direction because we had the x's in there. So that's, you would do that, and then you would say, okay, everything in the y direction plus upwards is fry equals f1y plus f2y plus f3y. Either way is valid. You get to choose. You're probably going to switch back and forth depending on the particular problem and what is easiest to do in that problem. And on the previous slide, I was just talking x and y. Now we add z. You have to have a right-hand coordinate system. All of science uses a right-hand coordinate system. I was once watching an interview with a potential professor that we were interviewing who used a left-hand coordinate system on their interview. That was just like, not getting the job, out, right? Because there's no such thing. We don't really use a left-hand coordinate system. What does a right-hand coordinate system mean? I'll tell you what the book says, and then I'll tell you what I do, okay? So what the book says is that you put your fist like this, your fingers curl from x to y, okay? Your fingers curl from x to y. It has to be the right hand, by the way, otherwise it wouldn't be right-handed. Fingers curl from x to y, and your thumb is z. What I like to do is just stick my fingers out at a 90 degree to my arm, and then fingers, arm, thumb, x, y, z. And you can move it in whatever direction you want. That's something we're going to have to get used to in this class, is that x is not always to the right. Y is not always up. We're going to have to learn how to take coordinate systems and move them, but still make sure that they're a right-handed coordinate system. Okay, with z, we're just going to take our a. We have a picture of a vector a. It's the blue vector down there. And we can fully define a in multiple ways. The first way is Cartesian vector notation, which will say a as a vector is equal to ax I plus ay j plus az k. A little bit in the x, a little bit in the y, a little bit in the k. How would I find the magnitude of that? Square root of the squares. A as a magnitude, there's no harpoon, so that's just a number, is equal to the square root of ax squared plus ay squared plus az squared. Notice that's a full scalar equation there. Okay, that's one way to identify vectors in 3D Cartesian space. Another way is shown on this same picture. This gives magnitude and direction, because if we're starting at the origin, we could walk a certain distance in the x direction, a certain distance in the y, and a certain distance in the z, and we would end up at the tip of A. Okay? You can kind of see that here. If I start at the origin, I walk this far in the x, and then I follow this little line in the y, and then I follow that little line in the z, I get to A. And that's what that's telling us. But there's another way to identify that same vector using coordinate direction angles. This might be something new. Maybe you skimmed over it a little bit in physics. Coordinate direction angles are simply the angle from each axis to the vector. So alpha is the angle from the x-axis to A, which is the vector we're concerned with right now. Beta is the angle from the y-axis to A, and gamma is from the z-axis to A. I think the confusion comes in is that each angle is in a different plane. Okay? We're in 3D. So you got to be able to kind of visualize those planes in order to come up with relationships of how we can go in between Cartesian vector notation and coordinate direction angles. So each one of these angles is in its own plane. Alpha is in the plane where the x-axis and the vector we're interested in exist. We can identify any plane with two vectors that are not in the same direction. And in this case, the plane we're identifying has the x-axis and A in it. Okay? That's where alpha lives. Beta lives in a plane with the y-axis in A. And gamma lives in a plane with the z-axis in A. Okay, so a couple questions for you. Where's the x-axis in my drawing? Straight this way, straight horizontal, right? This is now the x-axis. I'll draw it black. This would be x. This one right here. Okay? Where's the z-axis in my drawing? It's not straight up. That's a common misconception, right? What happened to the z-axis? See, I moved my head, and I took this whole thing and I leaned it up. What's z doing now? Z would be kind of shooting off the back at an angle, right? So straight up is not z. This is not the xz plane that we drew. It's the x something plane. This one right here is not z. It is the line right here, and I'll turn it red. This line right here. That's the red line is right here. See how I tilted that back? And now z is kind of off the back. I know this is challenging, but it's being able to visualize 3D objects and rotate them is a skill that can only be learned through practice. So the more you do it, the more that you kind of doodle and say maybe this, maybe that, the more it becomes clear. Okay, so why did I do all this? Now, coordinate direction angles are easy if I drew them on this plane, right? Can you give me an equation that would relate these three? The way I drew this is a 90-degree angle. Can you see the 90-degree angle up here? It's even labeled. This is a 90-degree angle right here. It doesn't look like it because you're not looking at it directly on. So now that we know that's a 90-degree angle, what's the relationship between A, AX, and alpha? Cosine of alpha is equal to AX over A. Always. That equation holds always. It doesn't matter what problem you're working on. It doesn't matter what situation you're in. If we know the x component of that vector and we know its magnitude, we can find alpha. If we know alpha and we know its magnitude, we can find ax, and so forth. Always. So let's do beta. I'm going to do the same thing. I'll give you a couple of seconds to draw yours because practice makes perfect. So go ahead and look at beta. Oh, before I freeze it, what we want to do is, this one I think is a little bit easier. Picture kind of standing below the axes and looking at it. So you're kind of a person standing over here, staring at it 90 degrees directly perpendicular to the plane. And see if you can draw what that plane would look like. And while you're at it, try to draw the gamma plane as well. So for gamma, you're kind of looking at it from over on this side, staring straight onto that. Okay, so once I have those three drawn, the relationship becomes simple. In the pictures above, the relationship is harder. Down here, the relationship is much simpler, right? It's the same equation for all three. The cosine of beta is equal to the y component of A over its magnitude. The cosine of gamma is equal to the z component of A over its magnitude. Does that make sense? Okay, so these can be challenging, but if you remember those equations and you remember that it always holds true, you can always relate a vector to its coordinate direction angles and vice versa. Okay, these can be hard. We're basically doing visualization, and we're trying to figure out how to visualize 3D space on a 2D plane, because the piece of paper is a 2D plane. One thing that I would highly recommend is don't ignore the little lines. What I mean by the little lines are these guys right here. What do you think this is telling us, this little line? Parallel to the x-axis. That is parallel to the x-axis, and what's this one? Parallel to the y-axis. So that means this 30 degrees is in the x and y plane. Very good. How about this 45 degrees? What plane is that in? Z and unknown. Okay, it's not the zx plane. How about this one over here? What's this 30 degrees in? Zx plane. So let's do F1 first. Our givens, we have a few on there. F1 is equal to 300 newtons. F2 equals 500 newtons. Then we have some angles in there. I'm going to leave those just on the picture. If this is my homework, I would make sure I drew a picture that clearly showed those. And then I say find the magnitude and the coordinate direction angles of the resultant force acting on the hook. How am I going to write that down? Well, what's the magnitude of the resultant force? F sub r is generally what we use. What's that? Well, it asks for the magnitude, right? Determine the magnitude and coordinate direction angles of the resultant force acting on the hook. So we're not supposed to find F as a Cartesian vector. We're supposed to find its magnitude and give its coordinate direction angles. So under find, I just wrote the magnitude, right? FR with no harpoon means magnitude of FR. And then what else are we supposed to find? Alpha, beta, and gamma, the coordinate direction angles. You could subscript those R if you want, just to, keep clear what alpha, beta, and gamma there are. Let's do some observations. We've already talked about a few of them, but what are you guys thinking? What's going through your head about how to solve this problem? Components of what? For what vector? F1, okay. So we'll need F1 as a Cartesian vector, right? That means x, y, z components of F1. We will also need F2 as a Cartesian vector, right? And then we're probably going to find FR as a Cartesian vector. And what would we do from there? As we had FR, we'd find its magnitude and then coordinate direction angle. So we have a path. So let's start with the first step. What are we going to do with F1? So I'd put in 30 degrees. One thing that there's a few things I'd really like to see on these drawings because they're going to help you. First off, every vector needs an arrowhead. If it's just a line, it's not a vector, okay? So you notice I have the arrowhead on F1, but I also added arrowheads on F1x and F1y. That's the activity we're doing right now, is we're breaking up a vector into its two components. By drawing these, I can make sure that I'm doing a proper tip-to-tail relationship, because that can be a mistake that's made sometimes. Maybe you have two vectors, but maybe you're using negative F1 instead of positive. So it's really a good idea to have the arrowheads on all of your vector drawings and also label the sides, okay? Once I draw this, I can shift gears in my head and I can just say trig time, right? Because I got my picture done. Now it's trig time. I got a right angle here, and I can get those values. Does that make sense? Okay, so go ahead and try to do the same thing for F2, but I had a really good question about F2. Which of the two planes should be drawn first? Because the pattern that we did was we started off with what we knew and started walking towards what we don't know, okay? What do we know? I mean, we know two angles, but how many magnitudes do we know? Just one. And which plane is that magnitude on? The green one. So we always walk from what we're given to what we know. Since we know one of the sides of this triangle, I would definitely draw that first. So we don't know any of the sides of this triangle. Okay, so that's the first plane. Does everybody have that on their paper or something similar? That's the greenish plane over here with the 45 degrees. I've labeled one side F2Z, right? F2Z is this side right here. Straight up and down. It's parallel to Z, so that one's clear. What's the top side? Is that a component of F2? F2XY is what I call it, because it's not on the X, Y, or Z axes. It's on the XY plane, but it's not parallel to the X, Y, or Z axes, right? So this is kind of like a temporary step in finding the coordinates. You're not actually going to use it in later calculations. It's a temporary step. I call it F2XY, and then we need to solve for it. Where am I going to use that? The next step, right? The next triangle that I draw, I need to know the value of F2XY because that's going to be the hypotenuse of the second triangle. Okay, I know some of you are far beyond this, but I want to make sure we're all kind of marching along here. So I just solved for F2Z and F2XY, and that's what I got. Everybody with me? Now what? I have to draw that gray triangle on the top, right? I have to draw this triangle right here. And the key to that triangle is that the hypotenuse is no longer F2. What's the hypotenuse of that triangle? F2XY, right. So I'm going to go ahead and draw that one as if I'm looking at it from straight above. It's in the XY plane. I want to look at it from straight above because that's what I chose. I could look at it from below too. Doesn't matter as long as you can draw it. If I look at it from straight above, it's going to look like this. I should make that green. f2xy. And then I'm going to have a red component that I'm drawing on the top there and a blue component. The red component's going to be f2y. And the blue component's going to be f2x. This is 30 degrees. Any questions about that? How I got that? Okay, so I have F1 and F2 written up here. Hopefully you can read that. I know it's a little bit small. Notice how F1 just has a cosine and a sine in it because there's just one triangle to take care of. But F2, we've got the x component and the y component. They both have a cosine and a sine in them because we had to get that F2xy, right? F2xy was the 500 newtons times the cosine of 45. And then we multiplied by the sine of 30 and the cosine of 30 to get those. Okay, so now we have, all of that work we just did was for what? What were we trying to get? No, not the result, not yet, right? All that work was just to get F1 and F2. We needed F1 and F2 written as Cartesian vectors. Now what do? We get FR. This is the easy part. Getting FR is the easy part. FR is just add the i's together and add the j's together, add the k's together. That's all. FR ends up being 436.58I plus 306.19J minus 503.55K newtons. Done, right? Sort of done. Is this what the problem asks for? Square root of the square. So now FR as a magnitude, which is one of the finds, this is the really nice thing about writing out your work. I can go back to the beginning of my work and I can say, I just did a whole bunch of work and I'm forgetting what I need to find. It's written right there. I need my FR and I need my alpha, beta, and gamma. So the first thing I'm going to do is find my FR, which is just the square root of all these things squared. And my FR ends up being 733 newtons. I only round at that last step there. Right? I haven't rounded the whole rest of the time until there. Okay, so now I'm almost done. And just to let you know, we should probably also write this out and then round after that. So that's what you get. Then you write your first answer, 733 to 3 sig figs, and you box that answer. But that's not our only answer. What do we need now? Angles. So how do we find alpha? You guys remember that equation? Cosine of alpha is ax over a, or in this case, frx over fr, which would be, what's frx? 436.58. I'm getting it directly from Cartesian vector notation, getting it directly from there. That over its magnitude, which is 733.43, newtons and newtons. Newtons cancel out. The cosine of alpha is equal to that, so alpha is going to be equal to the inverse cosine of 436.58 over 733.43. Alpha equals 53.5 degrees. Okay, any questions about that? Oh, 2:30. I guess I'm right on time. How would I get beta and gamma? Same. I would take the inverse cosine of the y and z components over their magnitude.